Hi, in this video we're looking at systems of equations. Our objectives include solving a system of linear equations with substitution, then we'll solve a system of linear equations with elimination, we'll solve a system of linear equations with 3 unknowns, and finally we'll solve a system including at least one nonlinear equation. So we start with solving a system of linear equations with substitutions, and a recall from some algebra. A system of linear equations has 3 possible outcomes. We can get one solution. That's when we would have lines that intersect in a single point. We can have no solutions, and those would be our parallel lines that never intersect. Or we could have infinite solutions, or you might see infinitely many solutions. And for that one, we actually have the same line, or 2 different equations that represent the same line. Right, so all the points are in common. We have infinitely many solutions. Note, to be a solution to a system of equations, the solution must satisfy all equations in the original system. And you could think just both for the original ones here, but we'll move into larger systems. So we want to just think it must satisfy all of the equations in the original system. So for number 1, we want to determine if the following points are solutions to the system given here. Y equals x minus 1 is the first equation, and y equals minus 2/3 x plus 4 is the second. So we remember that our points are x, y pairs, and we can just substitute in to see if they are solutions. So I'm going to write here 5 equals 6 minus 1. 6 minus 1 is 5, so this one checks out. It is a solution to the first line. For the second line, I'm wondering if 5 is equal to, I've got a negative 2/3 times my 6 for my x plus 4. If I do simplify the left-hand side here, my 6 and 3 would give me a 2 and a 1. And the negative 2 times 2 would give me a negative 4. Negative 4 plus 4 is 0, which is not equal to 5. So this would not be a solution. Right? It satisfied the first equation, but not the second, so it doesn't satisfy both or all solutions. For 3, 2. We can plug in our 2 for y equals 3 minus 1, which is 2. So it checks out in the first equation. And the second one, with a little more work here then, and here we could say first equation, second. Maybe I could have labeled that better for you. But this is looking at our first equation again, nice easy computation. And then for our second, we'd have a 2 equals negative 2/3 times 3 plus 4. And for that one, if we start simplifying, those 3's will divide out. So I get a negative 2 plus 4 on the right, which is 2. So I have that 2 equals 2 there. It checks out in the second as well. So yes, this is a solution. And it satisfies both equations, or it is a solution to both of those equations separately, which means it's a solution to the system. For C, if we check in our first equation, we've got 6 equals negative 3 minus 1, which is negative 4. We know that 6 is not equal to negative 4, so we're done. It's not a solution. We don't have to go to the second one and check. It already failed in the first. Right? It has to satisfy all those equations. So if even one of them fails, not going to be a solution. All right, for our actual solving, we have this substitution method. Our first step would be to isolate one of the variables from one equation. So we solve for x or solve for y. Our second step would be to substitute the expression found in step 1 into the other equation. Very, very important. You get a lot of people in calc with weirder functions, but who solve for a variable and then substitute it right back into the equation they used to solve. That's not going to do anything for you. We already know where that one came from. You will solve then the resulting equation. 4, then you'll substitute the value found in step 3 back into the equation from 1 to find the value of the remaining variable. And then you're going to check the solution in all equations to verify it is a solution to the system and write the answers in ordered pair in set notation. So just like that, x, y. Okay, so for 2, we're solving the system of equations using the substitution method. Our first equation, 3x plus y equals 13, and the second one is 2x plus 9y equals negative 8. Since I've got that leading coefficient of 1 in front of my y in the first equation, that's the one I'm going to solve for a variable. So I have 3x plus y equals 13. I can subtract that 3x on both sides to solve for or isolate y. So y would equal 13 minus 3x. I can take that whole expression then for y and substitute it in to my other equation. So I'm going to get a 2x plus 9 times 13 minus 3x, and that's going to be equal to negative 8. I can distribute through, so I get a 2x plus 9 and 13 would give me 90 and 27, a 117. 9 and negative 3, a minus 27x equals negative 8. I can combine my like terms, 2x and minus 27x, and subtract my 117 to move it to the other side. So 2 minus 27 will give me a negative 25x equal to minus 8 minus 117 and negative 125. And when I divide by negative 25 to solve for or isolate x, I find that x is 5. So I want to take that value now and substitute it back into this equation that I originally solved for x or for y, so that I can solve for or find the value for y now. So y equals 13 minus 3 times 5, which would give me a 13 minus 15 or negative 2 for y. So my proposed solution here is the point 5, negative 2. That's in my set notation. And I just want to check it now in both of my original equations like we did for number 1. So I'm going to put a 3 times first equation, my 3 times 5 there, plus negative 2 should give me 13. That's a 15 minus 2, which is in fact 13. So I didn't make a mistake. Looks good there. And for the second one, just to confirm, I get a 2 times x is 5 plus 9 times negative 2 for my y should give me negative 8. I get a 10 minus 18, which is negative 8. And you can see it checks out in both equations, so it is the solution to our system. All right, we're going to solve the same one, but with elimination. So note, our 3 options for solutions remain the same with the new method for solving, right, this elimination method. We have some steps here, write both equations in standard form for linear functions. That's our ax plus by equals c. Really, we just want x and y both on the same side for these solves. For 2, multiply one or both equations by non-zero constants to create opposite coefficients, like 2 and negative 2. So that when we add together, we'll zero them out. So that's step 3. It is to add the equations from step 3 to eliminate one variable. 4 would be to solve for the remaining variable then. And then we substitute that known value in step 5 into one of the original equations to solve for the other variable. And then we check the ordered pair in all equations to verify that it is a solution to the system and write the answers in ordered pair in set notation. So for 3, we set it up slightly differently, but same equations, I promise you. Solve the system of equations using the elimination or addition method. So in this one, we had y equals 13 minus 3x and 2x plus 9y equals negative 8. Because that first one has been given to us in a different form, we're going to add that 3x on both sides so we can get it into the standard form, 3x plus y equals 13. And then our second equation was the 2x plus 9y equals negative 8. Now you're welcome to eliminate either variable, x or y. Generally, you'll try an easier one, so you only have to multiply maybe one equation by a value instead of both. Like here, since we have prime numbers in front of the x, the 2 and the 3, we'd have to multiply the first equation by 2 and the second equation by negative 3 to get opposites there. But if I work with the y's, since I have that 1 in front of y here, I can just multiply the whole first equation by negative 9 on both sides to get my opposites for the y's. So if I do that, I get a negative 27x minus 9y equals that negative 117. And then my 2x plus 9y equals negative 8 is still there. My new step now is to add those two equations together. So the negative 27x plus 2x gives me my negative 25x. My negative 9y plus 9y is going to zero out. And I just get that negative 125 on the other side. So that, just like when we did it with substitution, if I divide by negative 25 here, I find that x is 5. I can go back into either of my original equations to solve for the second variable. But the first one in this case is solved for y already, 13 minus 3x. So I'm going to take that 5 that I found. I'm going to substitute it in for x over there. And we're going to say y is equal to 13 minus 3 times 5. And so when I do that subtraction again, I get a 13 minus 15, or negative 2. Because we've already checked this one, I'm not going to do that again. We know our solution set is 5, negative 2. And if I could draw nice curly braces, I'd have that set notation there. So just this single point is the solution set for us. All right, solving a system of linear equations with 3 unknowns. Note we still have 3 options for our solution set, but the geometry is different with 3 variables. So for our one solution, we're really in like 3 dimensions now. So you can think this is where like a floor meets 2 walls. So we have a corner of a room, or maybe 2 walls meet at the ceiling sort of thing. But still just that one solution, we meet in that corner. We can have no solution. And this would be like parallel planes. Right, so they don't intersect. And then we can have infinite solutions. And think floor and ceiling for that no solution, right? They would never, hopefully never intersect. And then infinite solutions, you can think of just a wall and a floor meeting. So we're coming together over here. This whole line is going to be our intersection, right? So where the floor meets a wall. Maybe that helps. All right, so our system's with 3 unknowns. We want to write each equation in standard form. For 3 unknowns, it's an ax plus by plus cz equals d. We choose a pair of equations and eliminate one of the variables using the elimination method. Then we choose a different pair of equations and eliminate the same variable. That's the important part. Right? Once we eliminate the same variable twice, we'll get 2 equations with the same 2 variables, and that takes us back to what we were just doing above. So for 4, take the new equations created in steps 2 and 3 and solve the system as with 2 unknowns. Note, make sure to verify that your solution so far satisfies both new equations. You'll save yourself some heartache if you check at a few different steps. For 5, substitute the values of the variables found in step 4 into any of the original equations that contain the third variable and solve for that one. And then check the solution in each of the original equations to verify it's a solution to the system, and write the solution as an ordered triple in set notation. So we want to solve the system. These ones are long. It's important just to stay organized. Again, you can get rid of any variable you want. Any of them look pretty easy here. I'll use the y just because I've already got opposite signs. You can try solving for a different variable or eliminating a different variable. You should get the same answer regardless of how you go. Maybe a fun thing to practice after the notes. But we are going to take and call these equation 1, equation 2, and equation 3. And so to make my set of opposites, I'm going to do some work in my head first. And I'm going to say we're going to do 3 times equation 1 to get my opposite y's here, plus equation 2. All right, so let's do our work here. We'll get a 3x plus a 3y minus a 3z equals negative 3 if we multiply that whole first equation by 3. And then our second equation is the 4x minus 3y plus 2z equals 16. When I add those together, I'm going to get what we're going to call equation 4. It's going to be a 7x minus z, and it's going to be equal to 13. And then we're going to take 2 times equation 1, which is going to give us a 2x plus 2y minus 2z equals negative 2. And we're going to add that to equation 3. Right? So we don't want to do the same two equations. We want a different pair. Here we have E1 and E3. E3 had a 2x minus 2y minus 3z equals 5. And when we add those together, we'll get a new equation. We'll call it equation 5, which should also have x's and y's. We get a 4x minus 5z equals 3 there. And if you do happen to eliminate two variables, and maybe we end up with just 4x equals 3 or something there, then we just simply solve for x, sub it into the other equation to solve for z, and sub both into one of the originals to solve for y. But most of the time, we'll have the 2 variables left over. And if we've done things correctly, we're now working with a system of 2 equations and 2 variables. So I just want to solve with equation 4 and equation 5. And so my easiest way maybe to do that here, I can just leave it over here. We're going to do a negative 5 times equation 4 to give us a 5z. And we're going to add that to equation 5 to eliminate my z's. I'm going to get negative 5 times equation 4 would be a negative 35x plus a 5z equals negative 65. And then my equation 5 was a 4x minus 5z already equals 3. And so I'm going to end up, when I add those together, with a negative 31x, my z's 0 out, equal to a negative 62 here. And it looks like it's working out nicely, so we probably haven't messed up. But it is possible to get fraction answers, so don't assume just because you did not get a whole number that you did something wrong. But usually if we do get a whole number, we're on the right track. So here x would be equal to 2. And so now that I got 2 for x, I can take it and substitute it back into either equation 4 or 5 to solve for z. 4 looks slightly easier, so I'm going to take my x equals 2 there, and I'm going to substitute it into equation 4. So I'm going to find here that 7x, or 7 times 2, minus z is 13, which gives me a 14 minus z equals 13. If I subtract my 14, or here, let's do it this way. Let's add our z to get it positive, and subtract our 13 on both sides. And I find that 1 is z, or z is 1. So we should check that in the other equation first. Since we used E4 there, we're going to check in equation 5. Hopefully we have x and z here right before we move on. So I get a 4 times 2 was my x, minus a 5 times 1 is my z. We're hoping that's a 3. 8 minus 5 is, in fact, 3. So it looks like we're on the right track. And so now we can take the 1 we got for z and the 2 we got for x and substitute it back into any of our first 3 equations to solve for y. The first equation looks the easiest, so we'll just go in there. So I'd get a 2 plus y minus 1 equals negative 1. 2 minus 1 is going to give me a 1 plus y equals negative 1. And when we subtract that negative 1, we find that y is negative 2. We used the first equation to solve for it, so unless you made mistakes in your tiny calculations there, you don't really have to check it back in that one, but you can always do it quickly. 2 for x minus 2 for y makes 0, and if z is 1, we get negative 1 equals negative 1, so that works. But we definitely want to check it in the other 2 that we haven't used. So in E2, I've got a 4 times 2 minus a 3 times negative 2 for y, plus my 2 times 1 with z, equals 16, hopefully. So we get a 16. We get an 8 plus 6 plus 2, which is, 14 plus 2, 16 equals 16. So we're good to go in equation 2. And then equation 3, we have a 2 times 2 for x minus 2 times negative 2 for y minus 3 times 1 for z, and we're hoping that gives us a 5. We get a 4 plus 4 minus 3, which is 5. So we check out in both of our equations. And again, we use that first one. We did kind of the mental check there, but our solution to the system is going to be the order triple. We have a 2 for x, a negative 2 for y, and a 1 for z. So again, you can retry it, eliminating a different variable. You should get the same answer. It'd be really, really good practice. But we'll spend some more time in here solving systems including at least one nonlinear equation. So we start with a note: a system of equations in which at least one equation is not linear is a nonlinear system. Recall, to be a solution to a system of equations, the solution must satisfy all equations in the original system. That doesn't change when we have nonlinear ones. In fact, it'll be even more important to do your checks here. We want to determine, just the same way as we did before, if the following points are solutions to the system. That includes x squared plus y squared equals 25 and y equals x squared minus 5. So negative 3, 4 for our first xy pair. If we sub those into here, I like the E1, E2 made it easier for me to do the checks as well, I think. So if I sub into equation 1 here, I get a negative 3 squared plus a 4 squared, and we're hoping that gives me 25. 9 plus 16 is indeed 25. Might remember doing that with a lot of your Pythagorean checks. And then we can check equation 2 as well. I would have that 4 is equal to a negative 3 squared minus 5. So 4 is equal to 9 minus 5, which is 4. That one checks out, so yes, we have a solution here. And for 3, negative 4, if I sub into equation 1, I'd get a 3 squared. If I can draw a 3, I get a 3 squared plus a negative 4 squared equals 25, which gives me a 9 plus 16 again. When I square, I get those positive values, and 25 is still equal to 25, so that one's good. In equation 2 here, I get a negative 4 equal to a 3 squared minus 5, or negative 4 is equal to 9 minus 5, which reduces to 4, and negative 4 is not equal to 4, so no, we do not have a solution here. The idea with the graph here is just to get you used to graphing, right? With the note below, graphing can help determine how many solutions to expect and weed out extraneous solutions. So we have a circle centered at 0, 0 with a radius 5 for the first one, so I'm kind of sketching in my circle quickly. Close enough. And then we know our second equation here is a squaring function or a parabola that's just been shifted down 5 units. So I'm down here again, and then I'm opening up. If I had my solutions, it'd be like the square root of 2 or square root of 5 there, so 2 point something. And so we're opening up through this circle. And I drew it like trash. Generally, you're going to draw. Ooh, actually, this side's really close, so let's make it good. But your picture's not going to be perfect in general. And so we can see, oh, that's the 3, negative 4. But that's the side I drew really well. Over here, negative 3, 4, we'd probably also go through. We just showed it was a solution. But again, you'll get an idea of how many solutions. So we can see probably 3 solutions to this system. This one was very, very easy to draw, so we can see kind of exactly where they do intersect. Your drawing for your scale is not going to be perfect. We might not know it's exactly at 3, 4, but we can kind of see that we have a solution in quadrant 1 and a solution over there in quadrant 2, so we know what signs to expect for the values. Because of the symmetry for both of these, when we do find negative 3, 4 as a solution, we know 3, 4 is also going to be on both of these functions, so you can think about the even and odd and the y-axis symmetry here. But worst case, you just plug in and solve and check your answers at the end. So we're going to solve a few of these systems together to get used to what some of them can look like. This first one, x squared minus y equals 0 and x plus y equals 2. This first one is a parabola. Really, it's our toolkit squaring function. If we add that y over, we get just y equals x squared. So I'm going up through 1, 1 and 2, 4, right off the graph there. and then negative 1, 1, negative 2, 4 off the graph to the left there. And my second one is just a line. If I solve for y, I'd get y equals minus x plus 2. So I know it's got a y-intercept at 2 and a slope of negative 1. So down 1, left 1, down 1, left 1. And from the graph of this one, it looks like we can see both solutions. Right? Picked a nice easy one to start with. But it looks like, if we're making a guess, we're going through 1, 1. And then over there in quadrant 2, we should also have a solution at negative 2, 4. But let's solve to figure it out. So for nonlinear systems, you can still do substitution or elimination. Substitution is going to be used a lot more often because sometimes we won't be able to eliminate one of the variables. But this one's set up to show you elimination, so let's try it. We've got an x squared minus y equals 0, and we have an x plus y equals 2. You can see, hopefully, if we add those together, we already have opposite for the y's. What we need to remember is that x squared and x are not like terms, so we're just going to write x squared plus x. Our y's zero out again, and our right side would just be 2. So we've got a quadratic equation. We can subtract that 2 over to the left side to set it equal to 0, and then look to factor. Here we'd have an x plus 2 and an x minus 1 to give us that positive 1 left over in the middle. And so x could equal negative 2 or 1, which we kind of saw with the graph already. But again, generally your graphs won't be that nice. You won't get all the solutions. But we can sub into either equation now to solve. Linear one's easy to use. It won't square anything or lead to any weird extra stuff, so let's go there. We already had it solved for y, so y equals minus. We're going to sub in our negative 2 for x first. We get a plus 2 there. So negative or minus negative 2 is 2. 2 plus 2 gives us 4. So we got a 4 for y. That goes with the negative 2. And then we've got a y equals minus the 1 now, plus 2. Make sure you keep your x and y organized so you know which set goes together, right? The negative 2 goes with the 4. And for this one, we can see the 1, negative 1 plus 2 will give us a 1, goes together with a 1. So our solution set are the points negative 2, comma 4, and 1, comma 1. All right, we would want to check them in the other equation. So we can do our check down here in the corner. We can call the first one E1 again, and the second one E2. So if I check now, we used equation 2 to solve. So let's use equation 1 to check. I need my y4 to equal x squared, so minus 2 squared. 4 equals 4. We're happy there. And for my other point, I need 1 to equal 1 squared, which is good because 1 squared is still 1. You could, to be super safe, always use the original equations, the x squared minus 4 equals 0 and x plus y equals 2, just in case you made a tiny mistake when we solved to do our graphing. But hopefully you do those well and don't make mistakes. But again, worst case, go back to the original equation, sub them in. All right, for b, we've got y equals the square root of x and y equals x minus 2. Our square root of x, we can graph that toolkit function out at 1, 1 and 4, 2. The line y equals x minus 2, we can see we've got a y-intercept at negative 2 and a slope of positive 1 here. So if we do draw tons and tons of points, we can see that it goes through at 4, 2. And we expect that single solution here. But I want to show you a substitution here so we can kind of see what happens and talk about these extraneous solutions as well. We have y equals root x and y equals x minus 2. Both are already solved for y. So really we're just setting them equal, but you can think we're taking this root x that's equal to y and substituting it into our other equation. So root x equals x minus 2. And there's a couple ways we can solve this because we've talked about factoring with square roots. But the most common method is to square both sides to get rid of that square root. And when we do that, we end up with an x equals x squared minus 4x plus 4, as we've got to expand that binomial on the right. If I subtract my x over, we get a 0 equals x squared minus 5x plus 4, which we can then factor as an x minus 1 and an x minus 4. Right, that'll multiply to 4, but add to give us that negative 5. And so x, we find 1 and 4 for our values. So we only see one answer when we graphed, and there is only one answer here. But if we do square both sides, we see 2. And if we solved without squaring both sides, so we're back to that root x equals x minus 2. If we subtract over, we get 0 equals x minus root x minus 2. If we solve this one or factor with our square root of x instead, so we get a square root of x minus 2 and a square root of x plus 1, which gives me that the square root of x is equal to 2, or the square root of x equals negative 1. I can see that wrong answer much more quickly, right? The square root of x can't equal negative 1, so that's not an answer. If I did square both sides there, I'd get x equals 1, which is what we have on the left. If we square both sides for that root x equals 2, we end up with x equals 4, which is our other answer, or really our only solution for x here. If you do solve with that squaring both sides from the beginning, and we get this 1, 4, this extraneous answer, it takes us back to what we looked at in one of the previous standards, where if we square both sides of this original equation, we're looking at y squared equals x. That's that parabola that opens to the right. So when we are squaring and going up and getting this extra answer, it's looking at the bottom half of this parabola, right? And so that's why we're getting the second answer here at x equals 1. So always, always, always want to be mindful of checking for extraneous answers here. I used up all your space. You can maybe do a check at the top if you want to, or this one's pretty easy to do a mental check for. We can also see it on our graph, but our answer here would be 4, 2. Right, that's our only solution, so we want to make sure we don't include that point at 1, negative 1. It's not part of the original system, it's part of that squared system, right, if we're looking at that sideways parabola. But our only answer here should be 4, 2. If you sub it in, we take the square root of 4, it's just 2. If we sub it into the second one, 4 minus 2 is 2, so we are good to go. If you did go all the way to the check step for the 1, you can see it's our third time to maybe catch it as an extraneous solution. But if we end up trying all the way to the check stage, we're going to see that our square root of 1 does give us 1, right? So that one would work in the first equation. But in the second equation, we can see that we want that 1 that we got to equal 1 minus 2, but 1 minus 2 is negative 1, and so we can see that those values are not equal. So it doesn't work out as a solution if you make it to the check stage either. And I feel like I just talked a whole lot about this problem, but it's really important to check for those extraneous solutions with the nonlinear systems. And again, this is why the graphing can help us see about how many solutions to expect. All right, let's do a couple more, just doing the actual work, less of me rambling. For C, we have y equals minus x plus 2. We know that's a linear function. It's got a y-intercept at 2 and a slope of negative 1. So we can go back 1, up 1, or right 1, down 1. And we can graph that function. And our second equation is a parabola. It's an x with a y squared. So again, this is going to be one of those that opens left or right. If we add the x over and subtract the 4, we can look at this as an x equals y squared minus 4. So it's just been shifted 4 to the left, but still opens to the right because of that positive y squared. And so if we follow our normal scale there, we can kind of see one of our solutions. Hopefully we got one at 0, 2. And then it looks like we should have a second solution somewhere over here near 5, negative 3. Probably further out than that because we won't hit negative 3 until we get... No, it might work at 5. I don't know. Let's try it because that would be 9 steps away from our vertex. But let's try it either way. So I'm going to do, let's do substitution since we're already solved for y. All right, so we can take that x or minus x plus 2, and we're going to substitute it in here. So we get a minus x plus 2 quantity squared minus x equals 4. If I square that, I get an x squared minus 4x plus 4 minus x equals 4. If I combine my like terms and subtract my 4 from both sides to set it equal to 0, so I recognize that quadratic, I get an x squared minus 5x equals 0. And if I factor there, my GCF is x. I'm left with an x times x minus 5 equals 0. So x would be 0 or 5. And so, yeah, it looks like we might have hit both with that graph. But we want to confirm and also solve for y. So my parabola is already here. X equals y squared minus 4. Nah, that's my x on the wrong side. So let's use the line to find our values for y. So y equals, for my first one, I'm going to sub in 0. So I've got a minus 0 plus 2, which is just 2 for y. So if x is 0, y is 2. And for the second one, I've got a y equals minus, just a 5 there. Some of those parentheses don't really matter still. We're not substituting in a negative, but again, good habit. So we get a negative 5. Let's work down. Negative 5 plus 2, which is negative 3. So I do get that 5, negative 3 for my second. So my two solutions here, it looks like I've got 0, 2 and 5, negative 3. All right, we use the linear function to solve, so we'll check with the parabola. We want to make sure it works for both equations to be a solution to the system. So I'm going to sub in, let's use the original here, y squared minus x equals 4. I'm going to sub in a 2 squared minus 0 should give us 4. And 4 minus 0 is 4, so that one works. And if we check that second point, we'll get a negative 3 squared minus 5 gives us 4. And we get a 9 minus 5, which is 4. So checks out in both, and we can say, hopefully successfully, that both of these are solutions to our system. For the last one, for D here, we have x squared plus y squared equals 9, and xy equals the square root of 8. The first one is a circle with radius 3, right? So circle, our center 0, 0, radius 3. So we can go 3 steps in each direction and draw our circle in. And the second equation, maybe more familiar if we write it as a square root of 8 over x, is just our reciprocal function, but it's been multiplied by root 8. But that was one of our toolkit functions, just with a stretch. So we don't know maybe exactly where it'll be, but it should have a piece in the first quadrant and a piece in the third quadrant with that vertical asymptote at 0 and horizontal asymptote at 0. We've now seen more with the rational functions. But we expect 4 solutions, right? So something we can see from the graph without actually seeing the actual answers here. And then hopefully we can solve for some. So we just solved for y. So I'm going to take this and substitute into my circle formula, or the equation there. And so we'll have an x squared plus a square root of 8 over x, quantity squared, equals 9. And now we've got an equation with just x that we can solve. So we end up with an x squared plus an 8 over x squared equals 9. If I multiply both sides by x squared to clear out that denominator, I end up with an x to the 4th plus 8 equals 9x squared. And then I can move that 9x squared all to the same side. I recognize I am quadratic in form, just with a higher power. So x to the 4th minus 9x squared plus 8 equals 0. I can factor that with an x squared minus 1 and an x squared minus 8 equals 0. So we find that x squared is equal to 1 or x squared is equal to 8, which gives us x equals plus or minus 1, or x equals plus or minus our square root of 8, which is plus or minus 2 root 2. But we'll keep the square root of 8 for the computations. I think it makes things a little bit easier here. And we want to solve for y if those are our x's. We do have 4 answers. We expect 4 answers, so hopefully there's nothing weird or extra going on there. And if we do, let's see, I can use 4 colors. Let's say, let me write them separate here. So we're looking at 1, -1, root 8, and negative root 8. And we want to find the y's that go with each. So for the first one, I have y equals, right, I already solved for it there, my square root of 8 over positive 1, which just gives me the square root of 8. For the second, I've got y equals the square root of 8 over -1, which will just give me minus the square root of 8. For my third, I've got y equals our square root of 8 over a positive square root of 8, which is just going to give me a 1. And for the last one, y would be equal to our square root of 8 divided by a negative square root of 8, which is going to give me a -1. So my 4 solutions, if we haven't made any mistakes, are 1, square root of 8, -1, negative square root of 8, or we could put the -2 root 2. I'd forgive you here. What do we have then? A root 8 and a 1, and then our minus root 8 and -1. All right, so our last step would just be to check. I'm going to do it mentally because that's fun, right? So we're plugging in either a 1 or a root 8. Positive or negative doesn't matter. We're substituting into that circle equation, right, to check now. We just use the reciprocal function one to solve. So hopefully if we sub them back in, we'd get the same thing back. But if I'm subbing into that circle, if I square 1, I get 1. If I square the square root of 8, I get 8. And since I'm squaring both my x and y, it doesn't really matter which one I'm subbing into. 1 plus 8 is always going to give me 9. So all 4 of these check out here. And I do have my 4 solutions. Reach out if you got questions. Otherwise, try some stuff.